Hello, my name is Magnus Petersen. This is my tutorial number 14 on TensorFlow, and this is about the DeepDream algorithm. The Google developers have made an official tutorial, but I have seen at least 2 versions of this source code, and they are both very confusing. The problem is that these tutorials are very complicated, and as usual with TensorFlow material, they are not very well documented. I spent a day or 2 trying to understand what they were doing, and I'm actually not sure that they are doing what the author thinks they are doing. The code looks something like this, with almost no comments, and the variable names are cryptic. And here we have some functions that build a TensorFlow graph for something called a Laplacian pyramid, and it's just very hard to understand what is happening. And the Laplacian pyramid is used in one way here for smoothing and normalizing the gradient, but that is not used down here in the actual DeepDream algorithm. And as you see, there's not a lot of comments, and again, the variable names are cryptic and difficult to understand. So this just takes forever to try and understand. And if 1,000 people have tried to understand this, and each of them have wasted, let's say, just 3 hours, then that is 3,000 wasted man hours, just because whoever made this was too lazy to polish the code and explain what he is doing. And this is a very typical problem in TensorFlow, and there's a special place in hell reserved for people who program like this. And let me show you what it looks like. More than 600 open issues on GitHub. These are bug reports, these are people who are confused, who cannot figure out how to do even trivial things in TensorFlow, and some of them are even Google employees, and some of them are even working on the TensorFlow project. So this is what happens when you have a very complicated project and you don't take the time to properly design and document what you're doing. And I don't want to single out this DeepDream tutorial as it is a common problem in TensorFlow. Anyway, the official version of the DeepDream algorithm produces images like this. So if we take an input image like this, we get something like this, where the DeepDream algorithm has enhanced or amplified patterns in the image. But it's not really, you can't really see anything here. Maybe those are some legs and some dog faces here, and I don't know. It actually doesn't look so good. So let's see if we can do better. The overall idea with DeepDream is very similar to what we have done in the previous tutorials. So we take an input image and send it through some neural network, such as the inception model. And I have just shown a simple example here. In reality, the inception model has many more layers than this. So we send the image through the neural network, and at some layer, we calculate the gradient, which tells us how we should change the input image to maximize the values at this given layer. And we continue doing this maybe 10 times or 20 or 40 times, and eventually patterns will start to emerge in the input image. And it's hard to see here because the image is so small, but it is very easy to see when we get further below and look at the larger images. However, a problem with this is that the inception model was trained on fairly small images that were like 200 or 300 pixels in each dimension. So if we input a large image with a high resolution like 1,000 by 1,000 pixels or something like that, then the DeepDream algorithm will create a lot of small patterns in the image. So what we can do instead is that we can call the DeepDream algorithm recursively. So we start with the input image up here, then we downscale it, and we downscale it again, and we get a fairly small image here, and we send that image through the DeepDream algorithm, and we get a result here. Then we upscale the result so it is the same size as this image here. Then we blend the two using a weight that we haven't shown in this diagram here, and then we send the blended or combined image through the DeepDream algorithm again, and we get this result here. And then we do the same, we upscale it, and we blend it with the original input image, and we send that through the DeepDream algorithm again, and this is the final result. So what happens here is that the DeepDream algorithm will create some patterns in the images that are relatively larger because they're created on a small image. And as we upscale and continue to use the DeepDream algorithm, we merely refine those patterns, and we actually get patterns within patterns, and this will also become obvious when we see the large pictures below. The inception model we are using here is different from the previous tutorials for 2 reasons. The first one is that we can use images of any size with this model. And the second reason is that the model gives prettier pictures with the DeepDream algorithm. I don't know which version of the inception model it is because, surprise, surprise, the Google developers have not documented it. So I will just call it inception 5h because that is the name of the zip file. And it should be automatically downloaded from the internet, and it's about 50 megabytes. And I have put all the functionality inside a class with this name, so it is easy to reuse. So we just instantiate the model like this, and then we have a list of tensors for some of the layers inside the inception model here, and we have 12 of those. There are more layers inside the model, but these are the main ones, and it works fine with the DeepDream algorithm. So here we have a bunch of helper functions for image manipulation. Here we have for loading an image and saving an image, and they both use the peel library. And here we have a function for plotting an image, and it doesn't look very good if we use matplotlib, so instead we use the peel library again. And here we have two functions for normalizing and plotting the gradient, and we will see an example of this below. This is a helper function for resizing an image, and it can either take the target size as a tuple with the width and the height, or it could take a floating point factor, for example 0.5, to reduce the size by that factor in each dimension of the image. And again we use a peel library, and there's a slight complication here because it only supports 8-bit bytes, so we have to convert our floating point images to and from bytes. And now let's start and build the DeepDream algorithm. The inception model will take images of any input size, but the problem is that it will eventually run out of RAM because it might use many gigabytes. So what we're going to do is we're going to calculate the gradient for small pieces or tiles of the input image, and then we're going to combine the gradient for the whole image. And the helper function for doing that looks like this. And as we will see below, the problem is that when we have the edges or borders or the seams between the tiles, we get a visible line in the gradient for the whole image. And in order to avoid that, we need to offset the tiles by a small random amount each time we calculate the gradients. So we start by figuring out what is an appropriate tile size, and this depends on the size of the input image and the desired tile size, which is 400 by default. And then we set a random starting position for the x-axis, and then inside a while loop we add the tile size to the starting position to get the end position. And then we make sure that it is within the boundaries of the image. And then we do the same for the y-axis. So we start with a random position, and then inside a while loop, we add the tile size to the start position to get the end position. We make sure that they are within the boundaries of the image. And then we get a tile from the image. So we just use the slice of the array. And then we create a fit dig with this tile of the image for feeding it into the computational graph in TensorFlow. And then we run the TensorFlow session to get the gradient for this image tile. Then we normalize the tile because they may have very different values, and it becomes a more coherent gradient for the whole image if we normalize each of the tiles individually. Then we save the gradient for the tile into the gradient for the whole image. And again, we just use the slicing functionality for the arrays. And then we advance the start position for the y-axis, and we do the same for the x-axis. And eventually we're done, and we return the gradient for the whole image. And now we get to the function which does the main optimization loop for the DeepDream algorithm. So we take a reference to a tensor for a layer in the neural network, and we take the raw input image and the number of iterations and the step size for the gradient and the tile size for the tile gradient as we saw above, and then whether or not we want to show the gradient in each iteration. So we start by making a copy of the input image so we don't overwrite it when we start working on it. And then we use TensorFlow to get the mathematical expression for the gradient of the given layer tensor with regard to the input image. And this function is just a fairly thin wrapper around TensorFlow's function for getting the gradient, and it looks like this. So we are inside the inception5h.py file, and what it does is that it sets the graph for the inception model as a default one, so that inside this width block we will be adding to that graph. And we start by squaring the tensor, and you can try and remove this to see what effect it has on the DeepDream images. And then we calculate the average of this squared tensor, and then we use TensorFlow's function for automatically creating the mathematical formula and adding it to the graph for the gradient of the given tensor with regard to the input image. And this uses the so-called chain rule of differentiation. So now that we have the expression for the gradient, we want to follow this in a number of steps to update the input image. So we have a for loop and we calculate the value of the gradient, and then we do some manipulation on the gradient. And I would encourage you to try and experiment with different formulas here to see what the results are. But what I have made here is something that I thought looked nice in the final DeepDream images. So we're using a Gaussian blur on the gradient, and the amount of blur is increased during the optimization. And I blur with 3 different amounts, and then I add the blurred gradients together. And one thing you should also note, as I have explained here in the comments, I am also blurring the color channel, which means that later on in the optimization, the gradient becomes grayscale. And this means that we are retaining the colors of the original image. In the early iterations, the gradient will change the colors somewhat, but in the later iterations, it only changes the contours of the image and not the color. So once we have calculated the blurred gradient, we normalize the step size so it is independent of where in the network that we calculate the gradient for which layer and so on. And then we update the image by adding the scale gradient. And then we can plot the gradient if we want to do so. And that's it. That's the basic DeepDream algorithm. So if we go back and look at the flowchart, we have taken the input image and we are sending it through the neural network, and we are calculating the gradient for some layer tensor in the network, and we're using this gradient to update the image, and we do this in the for loop. What is not shown here in the flowchart is the blurring of the gradient, but otherwise this is the main idea of the DeepDream algorithm. So it's pretty simple. And now we will go on to show how to do the recursive deep dreaming that we show in this flowchart here. So the helper function for doing that looks like this, and it has the same arguments or parameters as the function above for doing the deep dreaming, but we have a few more. So we have number of repeats, which is a number of recursive downscalings, and this is actually -1. So if you give it the number 4 here, it will actually perform 5 recursive calculations of the deep dream algorithm. And then we have the rescale factor for each of those iterations. We scale the width and height of the input image by 0.7, and we do this recursively, so it's 0.7 times 0.7 times 0.7 and so on. And then we have the blend factor, which is a value between 0 and 1 of how much we add in of the original image before we do the deep dreaming. So the algorithm looks like this. If we are not at the bottom of the recursion, then we do the following. We start by blurring the image a little, then we downscale it, then we call this function recursively, and we subtract 1 from the number of repeats, and we use a downscaled image. Otherwise, all the other parameters are the same. And when that is done, we upscale the image and we blend it with the original image. And then we take it and feed it through the DeepDream algorithm. So that's the recursive algorithm here. So now let's try and use it. Because we will be adding things to the TensorFlow computational graph, we need to have an interactive session. And the first example image is this picture of me when I'm trying to learn TensorFlow, and the developers have not documented their code. And before we start using the DeepDream algorithm, we need to decide where in the inception model we want to do the deep dreaming. So we need a reference to a tensor for a layer inside the neural network. And if we go back and look at the flowchart here, and again, the inception model has many more layers, but in the first example here, we want the layer with ID 2 or index 2. So we want to maximize the values at this layer here by changing the input image. So we get a reference to that layer tensor here, and we see that it is a tensor where the first 3 dimensions are question marks, and this means that the number of images input to the inception model and the dimensionality or the size of those images can be arbitrary. But the output of this tensor will always have 192 channels. And what we want to do is maximize the average of all the values output by this tensor by changing this input image here. So we call the DeepDream function above like this. We give it the layer tensor that we just found and the original input image, and we want to calculate 10 iterations, and we give it a step size of 6.0. This is twice as much as we will use in the recursive algorithm, but you should experiment with different values to see what happens to the resulting DeepDream images. And we want to use a tile size for the tile gradient of 400, and we want to show the gradient. So this is the original image before the DeepDream optimization, and this is what the gradient looks like in the first iteration, and it's pretty hard to see, so let's go down to some of the other iterations here. Here you can see some artifacts where the tiles have been combined, so the limits or the borders or the seams of the tiles are slightly visible here, and you can also see them here. So the idea is that we choose the starting position for calculating the tiles randomly, so that these artifacts will not be in the same place in each iteration, because if they were, then we would be able to see it in the final image. And this is the gradient for the last iteration, and we can also see some artifacts here and here. And this is the DeepDream image after having performed 10 iterations. So it has added a lot of these lines to the image in a way that matches sort of the original image. So it's not just overlaid, it's like repainted using a texture that the third layer in the inception model likes to see. And also note that the colors are very similar to the original input image. And this is because we used the Gaussian blur on the gradient, and it would become grayscale in the later iterations of the optimization. Now the problem with this is that it is very high frequency content. So because the inception model was trained on images that were a fraction of the size of this image, the patterns it likes to see are very small for an image with this high resolution. So let us try to use the recursive algorithm instead. So we call it like this, the recurse optimize function, and we just need to set the number of repeats. So we set it to 4, which means we're actually calculating the DeepDream algorithm on 5 iterations, and we have the blending factor between original and DeepDream images set to 0.2. So we only blend in a little of the original images just to get a little of the details back into the image, and we set the rescale factor to 0.7. And I would again encourage you to experiment with all of these numbers here. Oh, and one more thing is that the step size for the gradient is set to 3.0 instead of 6.0 as we did above. So let's see what happens when we run it. And this is at the bottom of the recursion at the level 0. So we have an image that has been blurred and downscaled several times now, and it looks like this. And once we send it through the DeepDream algorithm, it looks like this. So now we get lines in the image, but they are scaled more appropriately to the image, because this is a size of image which is more natural for the inception model because it's similar to what it saw during its training. So we upscale the DeepDream image and we blend it a little with the original, and we send it through the DeepDream algorithm once again. And you see that the lines become more refined now. So the DeepDream algorithm is working on the same lines that we created in the previous level of the recursion. So these are big lines again. So let's do it again. We upscale and we blend a little with the original image, and we send it through the DeepDream algorithm once again, and it refines the lines even more. And we do the same again. We upscale, blend it with the original image, and send it through the DeepDream algorithm. And once again, it refines the patterns that we have created in the previous levels of the recursion. And now it also starts to add finer details, smaller lines. So we have patterns within patterns within patterns now. And this is the final level. And we do the same again. We upscale, blend a little with the original image. And here we have some kind of warning. I don't know why. And the final result of the recursive DeepDream algorithm is this. So we have patterns within patterns within patterns, but we have some dominating large patterns. And I think this looks quite nice. And you should again notice that the colors are very similar to the original input image because we do this blurring of the gradient. But compare this to the DeepDream algorithm without doing the recursion, which looked like this. So this one just had a lot of very fine details. And if that's what you like, well, then you can use that algorithm. But personally, I think I prefer this image here where we have used the recursive algorithm. So we can do the same process, but we can use a higher layer in the inception model. So here we have the 7th layer indexed by the number 6. And otherwise, it's exactly the same that we're doing. So this layer of the inception model apparently likes to see dog faces and eyes and fur and some weird abstract patterns. So what happens is that the DeepDream algorithm sees traces or hints of these patterns, and then through the iterations where we're using the gradient, we're asking the inception model, what is it that you're seeing? What would you like to see? And how can we change the input image so you see more of this? So that's essentially what we're doing, and this amplifies these patterns in the original input image. And once again, this is the result of using the recursive algorithm. So it starts out like this, and it starts adding patterns to the low resolution image here, and it refines it through the recursive iterations until eventually we get this image here. So here we do the same, but we take the layer in the inception model with the number 7. And now, instead of using all the feature channels of this layer, we only used the first 3 feature channels. So we want to maximize the average of the first 3 feature channels in the layer number 8, that is index number 7. Otherwise, it's exactly the same that we're doing. And the result is that we get the image with these sort of round patterns here. So that is what the first 3 feature channels in layer number 8 of the inception model likes to see. So that is what we have added to the image. And here we have done it for the highest layer in the inception model. So this is index 11 or the 12th layer. And we have just done it for the first feature channel, but you can try and do it for more here. But the high level layers in the inception model recognize so complicated patterns that when we use the DeepDream algorithm, it creates very complex images like this. This is just for one feature channel. You should try it for more. So now let's try on another kind of picture. So here we have by the artist Giga. And if you have seen the Aliens movies, he designed the original alien for those movies. So this is one of his artworks. And here's what happens when we use this image for the recursive DeepDream algorithm. So in the deepest recursion layer, we start to add in some patterns like this. And in the next level of the recursion, we get these patterns here. And then we get these patterns here. And then it becomes these patterns here where you can start to see that it is forming patterns within patterns, but the large patterns that we generated in the earlier recursion layers are dominating. And the final result of the recursive DeepDream algorithm is this. So we have nice, clearly defined lines and a lot of patterns within patterns. And I think this looks nice. And also note that the colors are mostly the same as in the original input image because of this blurring of the gradient. And if we use the same input image but for a different layer in the inception model, we get this. So this is a layer that apparently likes to see eyes because it has made eyes everywhere. And maybe you like this, maybe you don't, but that's what happens. And here we have a picture by the artist MC Escher, and he was famous for doing these kinds of artworks with complex patterns inside patterns and so on. So I thought this would be a fun idea to try. And notice that this is a black and white image, and this is the result we get when we use the image with a recursive DeepDream algorithm. And this is a bit hard to see, and maybe this should be post-processed in an image editing program like Photoshop or something like that. But if you look carefully, you can see that the DeepDream algorithm has added a lot of patterns, and it has refined patterns that were already there. So here we have a snail, and it has added some kind of maybe an eye here and some patterns to the snail. So some of this looks quite nice, like down here also looks quite nice, and this snake here also looks nice. And other parts are slightly confusing, like this fish here, which is now like 3 faces of dogs that are combined, like we have an eye here and an eye here and a nose here and a nose here, and the same here, eye, nose, eye or nose, and a face of a dog here as well. So this is what happens when we use the recursive DeepDream algorithm on a black and white picture like this. And I have made some suggestions for exercises, and there's really a million ways to make the DeepDream algorithm, so I would encourage you to try and experiment with the source code and see how it changes the images. And you can download the source code by clicking on the link below the video.